Hello everyone, welcome back to the one more session of multimedia system. Let us continue with our topic discussion, that is data compression. In the previous session we had discussed about the meaning of compression and decompression and the various understanding with respect to the compression and decompression process. We have also discussed about the types or a classification of the compressions, that is a lossy and the lossless compression. We have discussed about the entropy coding, source coding, and the combination of entropy and the source, that is a hybrid coding. We had discussed about the major steps that has been involved with respect to the data compression, and we have highlighted the concept of decompression also with respect to symmetric and asymmetric technique. And finally we had discussed about the important coding technique, that is a run length coding with the help of an example also. So let us continue our discussion. Now we will see the next coding technique, that is called the zero compression or zero suppression. Let us discuss about this zero suppression technique. It is also a way to store large array of numbers where many entries are zeros. Means this technique is very much suited when there is an array of data streams where more number of zeros are involved in it. It might be a consecutive zeros, that would be very much beneficial. So how does this compression technique works? Here we work by omitting the zeros, and instead of storing the indices along with the values of the non-zero items, less space may be used in the total storing properties. Means the more number of zeros can be reduced or omitted by using the indices of representing the sequence number of zeros that might be occurred in the continuous bit stream. And it only makes sense if an extra space used for storing the indices. It means it is smaller than the space used by not storing the zero values. Means here what happens is, here we are just replacing the number of occurrences of zero by an indices. That is the only amount of storage that's been reduced. Let us consider here with a series. Suppose we have a sequence of AN, a series of sequence. Here we replace the series with the token and the count of number of occurrences of 0. So next what we do, when we have count of number of occurrences of zeros, here we usually need to have a special flag. What is this flag? That denotes or represent the number of tokens or number of repeated occurrences of zeros. Now usually a flag is said to be a token. We represent it as F with respect to the sequence. So what we do here, let us take an example and illustrate. Consider an example. Here let us take a huge stream of data bits, 8, 9, 4, 2, 5. Okay, a random number. Along with that there is a huge continuous of data streams. Let us look. I don't write the n, but I'll continue some more. Let us consider how many zeros are there. So if we count like this, given the continuity, but I'm not able to write all those things. If there are 32 zeros, we need to use zero suppression. What does this zero suppression do? Here we have a flag. That flag is denoted by a flag symbol or a character, that is F. So F, that is followed by the number of occurrences of zeros are represented. Now with the zero suppression we write the same number as 8, 9, 4, 2, 5, because after 5 there is a continuous sequence of zeros. So we introduce the flag F. So how many zeros are there? 32. This is how we represent the compressed code. Now look at this. There are n number of bits, 32 0 bits, 34, 33, 34, 35, 36 and 37 bits. So here it is totally represented by 37 bits of storage information, whereas here 1, 2, 3, 4, 5, 6, 7, 8. So only 8 bits are used to represent such a huge sequence of number. So this is the suppression coding technique called zero suppression. This is mainly used only with respect to the concurrent occurrences of zero sequences. Next, we'll look into the one more kind of coding technique. We call it as vector quantization. We have seen what do you mean by quantization? How does quantization happens? So I'll just recall the concept. A sinusoidal wave is there, so we do the signal quantization. So this kind of technique is mainly best suited for the signal values. So these kind of signal values are quantized into 3-bit quantization, 8-bit quantization, 16-bit quantization and so on. So what we do here, this is called the quantization of the signal. So this is the peak. If the curve are supposed to come like this, we represent it with respect to the peak values and so on. So what we do here, what are we doing here is, there are 3-bit quantization. The similar values with this range with respect to 3 very close occurrence signals are combined to represent one value. This kind of technique is called quantization. So quantization is defined as a lossy data compression technique by which intervals of data are grouped. See, the intervals of data are grouped or binded into a single value. So what are we doing? These 3 bits are combined to form one single value, or it is called a quantum. So means what are we doing here? We are combining here. So these 3 are later combined and it looks like this, a single values. Again the crust. Now trough. So this is what the representation of the sinusoidal wave, its signal representation and after quantization. So this is called a vector quantization. So it is very much efficient coding technique to quantize signal vectors, mainly these kinds of signals. So what happens here? It follows two steps. The first step is called code book training. So what does the codebook training do, or what we do here is, sometimes it is also referred to as codebook generation, and second step is called the coding itself, means each values here is represented into a codebook, a kind of hash table where it represents its own indices. So when we combine it, it becomes one. While we decompress it or decode it, the same indices are used with reference to these values and it is decompressed. So that method is called codebook generation. Coding of these 3 values into one quantum is called codebook, and mapping that value into the reference sheet or a reference hash table is called codebook training or codebook generation. And the coding back into the, using the indices, getting back the original 3 from 1 is called the coding value. This is called the vector quantization. Next, we will look into the one more pattern of coding. We call it as pattern substitution. So what is this pattern substitution? The name itself is making the concept clear. Pattern substitution, making an alternative or substitution to a particular pattern. This is called pattern substitution. We'll look into it. It is used for text compression substitutes. So for a single byte of pattern that occur frequently, means a particular text pattern that would be occurring more frequently, those pattern can be substituted by a single bit of character. A combination of text which occur more frequently is been replaced. What are the different patterns that occur more frequently during our encounter is, you might have seen in any of the text document the word the, most commonly was the begin, word begin, the word end, it, if, that, this, we, and so on. If you start listing, it goes on. So these are the common text pattern or a sequence of words, okay, or characters that has been encountered or repeated many times in any of a text document. So in order to use the pattern substitution, what we use here is each pattern, okay, is assigned with a particular character. So there might, we can go up to 256 words. For the 256 words, we can establish a pattern or a character representing it. So what we do, we represent called M byte representation, was marking by representation. Now what we do, typically what we do here is, for the character sequence THE, we represent it, the M byte value as ampersand. So now what happens, the character sequence THE the would be encountered in a text document many times, probably hundreds of times. So it uses 3 bits of information, 1, 2, 3. Okay, internally when we talk about T as an ASCII value something, H as an ASCII value something, E as an ASCII value something. So that value of that amount of information should be stored. So what we do, instead of representing all these things, we mark the word 3 or we assign ampersand to this character sequence. So what happens during the coding? So during the coding, wherever we encounter the word THE the, this would be represented. So after encoding, when we try to decode it, so this word, wherever we see and or ampersand, the word THE the will be replaced back. So this kind of compression or is said to be pattern substitution. So consider begin. We can assign our own character sequence. I can assign this with a star symbol. Okay, wherever the word begin encounters, we represent it with the asterisk. Okay, so while decoding process, wherever we find an asterisk, it is been converted back into or replaced with the begin word. This kind of compression technique is said to be the pattern substitution. It uses very less amount of storage space when compared to the other techniques. So it is very efficient only for the text patterns. Okay, the first and foremost here, we should make a list of text sequence patterns that are more frequently encountered in any one of the text document. Those can be encoded with M byte with respect to the table. Those characters are replaced by these symbols. This is about the pattern substitution. Next is the next pattern that we are about to study is diatomic. Diatomic encoding. Now look at this word itself. The name itself says di, 2, atomic, and atomic is said to be smallest entity. So smallest entities of 2 are combined for encoding process. Name itself is making the concept very clear. It is the variation based on the combination of two types of data or combining two data types or two characters. So this technique determines the most frequently occurred pairs. In the previous compression technique pattern, a particular pattern that has been occurring more number of times in the document was analyzed. Here, a combination of two words, two letters that would be always seen in a text document is analyzed. Occurring of pair of bytes is assessed. Then when we talk about the studies have shown that 8 most frequently occurring pairs in an English language. What are those? Mostly we have seen the E, T, ET, the TH, A, S, and also you might have seen whenever we use the word Q, always it is followed by U. Query, quantum, quality. So it's a combination, you can see. So like RE, IN, and some of those things. So these are said to be the 8 main or more frequently used the combination letters. When you talk about combination, always ET is followed by either, Eaton, Esther, these kind of combinations. So they are said to be two words. So though combining of those kind of two words always will be represented with one character. So in the previous pattern matching, what we were doing, we were assigning to a particular word like the, begin. So we assigned an ampersand. For begin we assigned an asterisk. Now what we do here, the combination of two words. So in particular document it might be SA, we assign an ampersand. Like QU here, diatomic, 2 atomic units of letters. We assign it with a letter something or a character symbol like this. Any symbol can be used. Means what we do here, see the bit representation, 2 bits of information, but yes as an ASCII value of, of a combination of bytes. Here 2 bytes are used to represent this character. Here only ampersand has one ASCII value. So 1 byte of information is used to represent 2 bytes. So when we do this kind of coding, look at the amount of compression that we are doing in a whole document. So the combination of QI might be encountered 10 times or 100 times in a text document. So we are replacing it, the combination of bytes, with a single. So if for 100 times it has been occurred, it's a combination of 2. 100 into 2 bytes. But when we use a particular symbol to represent QI, it is represented by using only 1 byte of information into 50 times. So in this kind of technique, we can achieve an efficiency of 10% of total compression. So this is called the diatomic encoding technique. Next, we look into the one more kind of technique, coding technique, which is called statistical coding. Name suggests, so most of the coding techniques are very much accessible or analyzable by the name itself. Here, no fundamental reason that are different characters need to be coded with a fixed number of bits. Okay, a particular concept like fundamental concepts are not there. Here, what we do here, we use Morse code here. M-O-R-S-E, Morse code. What does it do? So what does it do is, it is totally based on frequency of occurring characters that are coded with short strings. Means there are few characters or sequence of characters that would be occurring more number of times in document, that would be always coded with a less sized string. So less occurring strings might be coded with a bigger character string. This is the statistics. So what kind of statistics we are doing? First thing, we need to find out the more frequently occurring characters in any of the document. Suppose you consider we are talking about the subject called operating system. Okay, when you talk about the operating system, the word operating system. So this combination of words might be repeated in a particular text document many times, hundreds or thousands of times, because the topic itself is an operating system. What we do? We do a statistical analysis, that is more frequently occurring characters. So this is the one character and this is one character that's been encountered in the text more frequently. So we represent this or this kind of more frequently occurring characters with a very short string like AA. Okay, so whenever we see a word operating, that is been encoded with AA. While decoding process, whenever there is a AA, it is obviously converted back into the word called operating. Like more frequently occurring words can be represented. I can represent as A1. When we decode it back during the process, A1 means system, we regain back. So this kind of representation is called statistical coding. Such statistical coding depends on how frequently individual characters or a sequence of data bits occur. So if there are some characters which are less frequently used, we can extend the length of the coding string length. So what we do here we mainly concentrate on the statistics. We make a statistic. What kind of statistics? The more frequently occurring characters. Then we keep on assigning the values to it or characters to it. So this is how the compression happens here. Then we will go into the one of the important compression technique, that is the Huffman coding. I mark it as star because it's a very important coding technique. So when we talk about Huffman coding, it comes under the category of lossless compression technique. When you say lossless, what do you mean by that? During the compression and after the decompression, there would be no loss, or the amount of loss of information would be very much minimal. So that kind of compression technique is said to be a lossless. So Huffman coding comes under the lossless compression category. It is totally based on binary tree that is the frequency sorting technique. Means here binary tree concept, you know that, I don't need to explain that. Binary tree with respect to the frequency of the occurrence of sorting is done, and it allows to encode any message sequence in shorter encoded messages. Means any kind of message. In the previous compression techniques, we used to see a pattern, we used to see a zero suppression or a diatomic, only two things, or the statistical compression where the more occurrence was finding out. There what we had, the compression rate, the rate of compression was very much less. So in one of the techniques we saw only 10% of achievement of compression, but whereas in Huffman coding we are able to achieve the compression rate to a very greater extent, and it allows to encode any kind of message irrespective of repeated pattern, irrespective of zeros or anything, in a shorter encoded pattern. So let us look into the algorithm. How does it work? Because in many of the question papers they were asked what is Huffman coding, or explain the Huffman coding with the illustration of an example. So, we need to look into the algorithm and practically demonstrate with an example. The algorithm goes like this. Very simple thing. First one, what are we supposed to do here in the first thing? Find the two smallest probability nodes. Find two smallest probability nodes. So, probability means the occurrence. Okay. Here in some of the papers, in a question paper, instead of using the word probability, even I have seen they are using the words called frequency. Like most frequently occurring nodes, more frequently or more probability of occurring. So both relies with a single meaning. The first thing is, in a given set of sequence, find the two smallest or the two frequently occurring nodes, valued nodes. Second one, what to do? Create a new node. With what? With the what we have found with the two nodes. So you need to combine, okay? Combine through the two nodes what we have found in the first step and make one more new node. After that, what we are supposed to do? Insert the new node to the list. Means earlier we had a list of nodes. What we did in that list of node, we tried to find the two most frequently or probably occurring nodes, the smallest value with the smallest values. That is important. Two smallest probability occurring nodes. We combined that node and made one new node, and that new node is added to the list again. What we do here? Again, we repeat the step. We repeat all the steps from the again find the next two smallest nodes in the new set. Again create one more node with the two smallest values, and that node is inserted into the new node again. So how long should we repeat it? We should repeat until last one node is left or present. So we need to carry out this process until the final one node is remaining. This is the algorithm. Let us consider with an example. If you consider with an example, we will be able to understand the concept. So let us start. Consider there are 5 process nodes. What are those? A, B, C, D and E. Okay. For the better understanding, I'll wipe out this so that I can have more space in order to explain the concept. So we have 5 nodes or 5 letters are to be encoded, and they have a relative probability. So all those probabilities will be mentioned in the question paper. Only when they mention the probability of each letter, we will be able to continue the Huffman coding. What are the probabilities? Let us look into it. Let us take down the values. So this is the list. So what is the probability of A? It is represented as P of A is equal to 0.16. The probability of B is equal to 0.51. The probability of C is equal to 0.09. Then the probability of D is equal to 0.13. The probability of E is equal to 0.11. Okay, this is given. Now we will be starting the Huffman coding. Let us recall the step 1 what we had written just now. It says find the two smallest probability or probabilistic node. Here, which is the two smallest node? Look at the values. Probability of A is 0.16, B is 0.51, 0.09, 0.13 and 0.1. When we look into those two, which is the smallest one? It is the C, and next one is obviously the D. Okay. Now let us look into the algorithm. Step 2. We have found two values. We need to combine it. So how do we combine it? So we will write it with a diagram here itself. That is, probability of C is equal to, what is that? 0.09. So you might be asking, sir, why are you writing probability of C in the left side and probability of E in the right side? See, the C has a lesser value when compared to the probability of E with respect to 0.11. What does a binary tree says? The rule of binary tree says always the lesser value will be in the left side and the bit higher value will be on the right node. So that's why the probability of C I have written here, and the probability of E, that is 0.11. What does an algorithm says? Combine those two nodes. So when we combine, we'll write it as probability of C and E. So we are combining it. So C and E is equal to, we need to add. So when we add these two, we get 0.20. Look at this, 9 plus 1, 10, 0, 1 carried. So it would come here 1 plus 1 is 2, so 0.20. What does the next step of algorithm says? Insert the new generated node into the list. Now what are the two things that we have made used? So, well, I will wipe out these two because we have made use of those things. So what would be the new list? So I will write this here. Probability of D. What was the value of D? It was 0.13. So what would be the new list? That is probability of C and E. So probability of C and E. What is the value? 0.20. See, earlier we had 1, 2, 3, 4, 5 elements. 1, 2, 3, 4. What we have now? 1, 2, 3 and 4. Means the size of the list is reduced. Now again we need to repeat the step. So what we do here again? Step 1. Find the smallest two probable elements. Now when we talk about smallest two in these, which is the smallest? See, look at this. 0.16 and 0.13 is the smallest one. So again, what are we supposed to do? We are supposed to combine those two and create one more new node. So when we combine those two, what would be the value? That is 0.16 and 0.13. If we add, what is that? 9 and 0.29. So even this would be in the same hierarchy. So there is no need of adding one more node or here and there. So instead of a upper node, so this would be of same hierarchy level. So what we do here? So what are we supposed to combine? First one, which is the lowest value? D. What is the probability of D? 0.13. I'll write here. Probability of D is equal to 0.13. Which is the next one? Probability of A. Probability of A. What is the value? 0.16. 0.16. What are we supposed to do? We are supposed to combine these two nodes and form one new node. What is that new node would be? Probability of D and probability of A. What is the probability of D and A? When we combine it, it is 0.29. So it's been created. Now what are we supposed to do? Now we are supposed to eliminate the used nodes and insert the new node that has been generated. What is the new node that has been generated? I'll write here itself. Probability of DA is the new thing with the value 0.29. What happened in the next step? In the previous step, we had 4 elements in the list. Now it has reduced to 3 elements. Now again, repeat the process. Find the 2 smallest nodes with respect to the probability. So it is here 0.51, whereas these two are 0.20 and 0.29. So it is better to combine these 2 nodes. So we'll look here, we'll calculate here itself in the side. So this is just a concept to make you clear. I am writing here. So 0.20 and 0.29. So obviously it would be 0.49. Means, look at this here. What is the level? 0.01 and 0.1 stream values are here. Whereas in this level, 0.2 stream is there. If it was 0.3, we could have made it a hierarchy level here. Now what is the next state of level here? What are we combining? We are combining these two itself. So when we combine it, it goes to upper level. So the new node would be here. It is P of CE along with DA. What is the value? We have seen here 0.49. See. Now again reduce the list. So these two are used, remove it. Now what is the only value that is being left? 0.5, that is the probability of B. So again we need to do it until the only one node is left. Now how many node is left? Here one node is there, here one more node is there. So 0.49 and 0.5 can be merged to form one single node. So let us take here probability of B here is equal to 0.51. So let us combine. Since we have made use of this node also, the list becomes totally empty. Now what happens with respect to the probability? The probability of CEDA and we are combining it with B. So what is the value? So very simple. Again you need to make a rough error calculation. Look here, 0.49 of node value of this one with respect to 0.51. What we get? 9 plus 1, 10. Here 5 plus 5, 10. What happens? 1 single number, our single value 1.00. Look at this. What we had stated in the algorithm last. This process has to continue until only one node is present. A last one node is being achieved. This is the representation of an Huffman code. Now we have got the complete Huffman code. So here even we can represent the value. Since it is a binary value, it is the values are represented as left as 0 and right 1. Why? A binary tree says left is always a lesser node value, so 0, right is a greater values 1. Again for this node, this is left 0, for this is right 1. Again for this node, this is left and this is right 1. For this node, this is left and this is right 1. Now complete representation has been achieved. So do you think that here we have completed the things? No. Here the final concept is left. Now when we have done the complete representation of a coding technique, that is Huffman coding, now we are supposed to mark or give the weights of these things. So how do we give up a weights? Weight is represented as W of A. So where is A? Look at this. A means from here to reach A, what would be the path? 0, 1, 1. 0, 1, 1. This is how we represent the weights. So next, W of B. So when we talk of W of B, look at this B here. Only one step we get. What is the path or a weight? That is only 1. Then weight of C. Where is C? C is here. So how do we reach here? From the root node 0, 0, 0. So 3 zeros. Then W of D. Where is D? D is here. How do you reach here? From here 0, 1, 0. 0, 1, 0. And finally W of E. E is here. 0, 0, 1. Look at this. Now we have received the weights. So using this coding, we represent the occurrences along with the different coding strategies of Huffman coding. This is called the Huffman coding techniques. So these are the different coding techniques I had wished to explain. So this is about Huffman coding. When they ask in the exam with respect to the probability of A, B, C, D, and they might give n number of nodes, and even they are supposed to give the probability stakes, and they might also ask the using the Huffman coding represent the different levels of compression with respect to Huffman, and also provide the weights for each node. So A, B, C, D and E can be coded in this format. So now when we talk about the A, occurrence of A, usually in ASCII it's a 4-bit characteristics representation. Now look at this. This sequence can be used only by representing with 3 bits. So B can be represented with only 1. So and C can be represented as 0, 0, 0. Okay, how ASCII value, when we know that the ASCII value, consider if the ASCII value for A is 0, 0, 0 or something, I'm not writing the exact ASCII value. So if B is followed by 0, 0, 1 and C is followed by 0, 0, 1, 0 and so on sequence, means 4-bit representation. Now all A to Z, all the characters are used by only representing the 3-bit representation, and here only a single bit representation is achieved. So when this kind of representation is converted from 4-bit to 3-bit representation, obviously the size can be compressed to a greater extent. So this is how Huffman coding is very much helpful without the loss of any information. Even when you compress it, the size would be reduced to a greater extent. Even when you decompress it, that is decode it, the original data could be retained back without any loss of information. So this is about the Huffman coding. So by the end of this session, before completing it, let us recall what we have discussed in this session. We had discussed about the various compression techniques. So first we have seen about the zero suppression techniques. Second one we have seen about the vector quantization, and next we had seen about the pattern substitution and the diatomic encoding, statistical coding, and finally the most important, Huffman coding. These are the topics I had wished to share in this session. Thank you very much.